Okay, here again is our second order differential equation. It's non-homogeneous because in the generic case, we may have some external forces acting on the system. And we have mass times acceleration here. We did all of the algebra that got us to this equation a couple of videos ago, but this first term includes our mass times acceleration. The second term is damping, and the third term includes the spring constant. The damping was 0 in the previous video because we looked at undamped systems. So I take this term out or send it to 0, then we have a second order differential equation that we can solve using the technique that we did in the previous video. But in this video, we're going to look at the case where this is not 0. So these are called damped systems or damped equations of damped motion, damped vibration. We are, though, going to continue for the moment looking at cases where there are no external forces. So we are going to be working with a homogeneous equation. But the fact that there's damping makes this situation much more realistic. When there's no damping, there's no friction, there's no air resistance, there's no medium resistance, water or oil, whatever the thing happens to be sitting in. But even air resistance, which seems negligible, plays a part, has an impact. And so if we say there's no damping, then we are quite literally saying that we're working in a vacuum. And that's very unrealistic. That doesn't actually happen. So we're going to be working with a damped system, which has this equation. And if I wanted to solve this homogeneous differential equation, the first thing we need to do is recognize that solutions look something like this, and then use the characteristic equation mr squared plus gamma r plus k equals 0. We're going to solve that equation to tell us what the r values are, no pun intended. So let's do that using the quadratic formula. We end up with r is equal to negative b, which is gamma, plus or minus the square root of b squared minus 4 times a times c, and that is all over 2 times a. Now remember that the discriminant here can either be positive, negative, or 0. So we're going to have three cases. If gamma squared minus 4mk is positive, if gamma squared minus 4mk is 0, and if gamma squared minus 4mk is negative. If the discriminant, just the thing underneath the square root here, if that thing is positive, then we're going to have some number plus the result of this over 2m and some number minus the result of this computation over 2m. So we're going to have two distinct real roots. If the discriminant is 0, then we'll get a number plus 0 and a number minus 0, which obviously is the same thing over 2m. So here we have repeated roots. And if the discriminant is negative, you end up taking the square root of a negative number. So you get complex roots. And remember that complex roots come in pairs. So we'll have two complex roots. Now I'd like to take a look at this situation in a little more detail, and we'll actually look at each of these in a little more detail, but we're going to start with this one. If we have repeated roots, well, if we have two distinct roots, distinct roots of the characteristic equation, well, the characteristic equation is just a polynomial. It's just a trinomial, a quadratic equation. So the graph of that is going to be a parabola with two x-intercepts. But in the case of the when the discriminant is 0, we have repeated roots, our parabola looks something more like this. And the vertex of that parabola is the single value that's repeated. That's the repeated roots. And I don't know if you'll remember this from algebra, but the x-coordinate of that point can be computed with negative b over 2a. And then, of course, the y coordinate would be what you get when you plug that in. But I'm really not interested in that, right? I'm interested in the r values that make this true. So I'm interested in the R value, which is my input value, and so that's my negative b over 2a. So R in this case is going to be, wrong color of pencil, R's, R1 and 2, are going to be negative b over 2a, which means my solution looks like this. The linear combination of a e to the r1 of t, where r1 is negative b is gamma, over 2a, a is m, times t, that's a e to the rt, plus b times t e to the rt, where r is the same value as in the previous term. So for this situation, when the discriminant of our characteristic equation is equal to 0, we know that our solution will take this form. And remember, we're working with homogeneous equations, so I don't have a particular solution to the non-homogeneous. I don't have that term tacked onto the end here. So this is the form my solution will take in the case that the discriminant of my characteristic equation is equal to 0. It's also worth noticing that if gamma squared minus 4mk equals 0, then gamma squared equals 4mk. And if I take the square root of both sides, I get gamma equals 2 times the square root of mk. We call this case the critical damping case, and you might see this notation here. This gamma value is critical. And for the purposes of record keeping, I'm going to move this over here. Gamma equals 2 root of mk equals gamma sub CR. That's the value of gamma that produces critical damping. Okay, now let's take a look at the case when the discriminant is greater than 0. I'm going to do a little bit of algebra here. I'm going to start by factoring out that gamma squared inside the square root. So if I factor that out, I get 1 minus, factoring is essentially dividing out. So I'm dividing out a gamma squared. So I get that. And then I can take the square root of gamma squared. That's just a factor now. So I get gamma plus or minus gamma times the square root of 1 minus 4mk over gamma squared over 2m. And I dropped my negative here. And then I can factor out that gamma. Let's factor out negative gamma. And let's factor out the 2m while we're at it. That leaves me with 1 minus or plus the square root of 1 minus 4mk over gamma squared. There are times when it matters whether your plus is on the top and your minus is on the bottom, or the other way around. In this case, it happens not to matter, so I'm going to go ahead and change that to the more familiar plus or minus. But actually, I wanted to do that just to bring your attention to the fact that sometimes it really does matter. And there is a symbol. We have the symbol plus or minus. There is also a symbol minus or plus, and it means just that. Okay, there are a few things we can observe about this version of our solution to the quadratic equation, the characteristic equation. One is that if I add 4mk to both sides of this equation, or this inequality rather, I get 4mk. I get gamma squared is greater than 4mk. So that means that the fraction I have down here, gamma squared, is greater than 4mk. The denominator is greater than the numerator. This fraction here is some number less than 1. More importantly, however, when I subtract this number from 1, I'm saying, or I'm going to get, some value inside here, right? 1 minus something is going to be less than 1. And that value is going to be, let's see, how will I do this? The value I get by doing that is going to be the entire value is going to be less than 1. The thing inside the quadratic, and the thing inside the square root there is going to be less than 1. Well, when you take the square root of a number less than 1, you get a number less than 1. So that means the entire thing, I'll highlight the entire square root, is going to be less than 1. So if this is some number less than 1, if I take 1 and add a little bit to it, something less than 1, I'm going to get something less than 2. More importantly, if I take 1 and subtract less than 1 from it, then I'm going to get some number less than 1, but greater than 0. And that means that this value here is guaranteed to be positive. If you take a positive value and multiply it by a negative value, then your answer is guaranteed to be negative. So both of my R values in this case, R1 and R2, are less than 0. They're both going to be negative. And my solutions, based on our previous work, will look something like this. A e to the R1t plus b e to the R2t, where a and b are constants. We've been using C1 and C2. I'm using a and b in this case. And R1 and R2 are the two distinct roots that we got from solving this quadratic equation, solving the characteristic equation. We get two R values by doing that if the discriminant is greater than 0. Now, why is it important that those two values are less than 0? It's at this stage, it's not something that I'm going to go into to discuss, but I'm going to come back to it. So I wanted to point out that while my solutions look like this, let me highlight them so they match the case that we're talking about. The R values are going to be negative, all right? So I'll come back to that in just a minute. Before we move to the third case, though, I want to remind you that we have this equation. Where am I? Use my pointer. This one right here, if I take the square root of both sides of that, inequality, I get the statement gamma is greater than 2 root km, or mk. And for gamma values that are greater than 2 times the square root of mk, we say that the system is overdamped, or we call this overdamping. So actually, I should make a note here. This is overdamped. And I'll add one down here. This is critically damped. And then, of course, we'll have one for the third case as well. So let's talk about that one next. We know we're going to have two complex roots, two different complex roots. And if I wanted to, I'm just going to do a little bit more algebra here. If I wanted to, I could write this quadratic equation solution this way. Gamma squared minus 4mk. I'm just splitting up the fraction. Because this is the piece here that's going to be a problem. This is the piece that's going to introduce the imaginary part of my complex number. So if I choose to call this number, let me use a highlighter instead. If I choose to call this value here lambda, yet another Greek letter for you, and I will call this value here, now this is going to have an I in it because I've said in this case, in case 3, this thing right here that's discriminant, the thing under the square root there, is negative. When I take the square root of a negative number, I'm going to get an I, right? So this number is something I, and I'm going to call it mu. So the I comes out of, comes from having taken the square root of a negative number, but the numerical value over 2m, that part is the mu. So this is like my a plus bi, but it's plus or minus. So I'm basically saying here that I'm calling R lambda plus mu I and lambda minus mu I. And that means that my solutions are going to take the form a e to the lambda t cosine of mu t plus b e to the lambda t times the sine of mu t. And if I factor out the e to the lambda t, I get a cosine mu t plus b sine mu t. And of course I can rewrite that as r e to the lambda t cosine of mu t minus delta. So let's summarize this as well. We have r values of lambda plus or minus mu I, where lambda, sorry, wrong pen, lambda is equal to negative gamma over 2m, and mu is equal to the numerical part of this divided by 2m, and then of course that's times I because this is negative. So we need to figure out what those are, and this is just sort of shorthand. And we have our solutions, u, in the form r e to the lambda t times the cosine of mu t minus delta. This is the same form of a solution as we came up with in the undamped system. That's kind of interesting. Okay, so I'll highlight my form of my solutions to go with case 3. And then let's also make the observation that since our gamma squared minus 4mk is less than 0, gamma will be less than 2 root mk, and we call this underdamped. Notice that the critical damping coefficient, gamma sub CR, this one has the CR on it. That's the value of gamma that produces a critically damped system. You can determine whether a system is critically damped, overdamped, or underdamped just by doing this little computation here. Take m and k from your equation, m and k, multiply them, take their square root, double the result, and if that number is gamma, then the system is critically damped. If that number is smaller, where am I? If that number is smaller than gamma, the system is overdamped. And if that number that you compute is bigger than gamma, the system is underdamped. Of course, you could also determine whether the system was overdamped, underdamped, or critically damped just by looking at the discriminant here. If you compute the discriminant and it's greater than 0, it's overdamped. If it's less than 0, it's underdamped. And if it's equal to 0, it's critically damped. So depending on whether you're going to solve this equation using the quadratic formula or not, you may already have that information. But if you don't, if you just want to look at the equation and determine its relationship to being critically damped, whether it's critically damped, over or underdamped, then you can do that quick calculation instead. M times k, take the square root, double it, and compare that to gamma. Now you might be asking yourself a very reasonable question at this point. What does it mean to be critically damped? What does it mean to be overdamped or underdamped? Well, let's talk about that a little bit. I'll go to another screen for that. When I was about 14, my father decided it was time to teach me how to drive. Now, my father, being who he is, did not sign me up for a driver's ed class. You couldn't do that at 14 anyway. He stuck me behind the wheel of his very large pickup. This was an automatic. I had never tried to drive a car before in my life before this instant. And so we got in the car, and I'm going to try to use a line here to vaguely describe the path that we took. We started, and as long as I was going slowly, it was okay. But then anytime I made a curve, I overcompensated, and then I overcompensated to correct, and then I overcompensated again, and then I overcompensated again. Eventually, I did figure out kind of what was going on. Now remember, I was 14. So after a few minutes, my path looked something like this. Whoa, 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 whoa. Okay, I get it. This is what we would call underdamped. In a way, you can think of it as being under restricted. The path is every what's the word you want? The word I want. Every compensation I made, every correction that I made was wild and way too much. And eventually I figured it out, and the path sort of slowed down and I straightened things out. So this is what it would look like if I was underdamped. Say that I was trying to get from point A to point B. I'll do that one in, let me redo that. I did it in pink, but I'm going to do it in green. Green for go. This is what our mapping softwares do, right? Your starting point is green, and your ending point is some version of red. So we'll do that. Now that's the underdamped version of my driving lesson. If things had gone very differently indeed, then I might have said, let's see, because I'm a brand new learner, a brand new driver, I'm still going to have to make some corrections. But those corrections are, I'm going to go more slowly. Those corrections are smaller and smaller and smaller until I get it. And it's unlikely that there would be no corrections, but there are no wild overcorrections, right? So this is what we would call critically damped. Now, underdamped would be a situation where, for example, I was just too scared. Whatever corrections I might make, I just couldn't get there, right? So the the underdamped situation, the under restricted driver doesn't have any control and eventually, hopefully, levels off. The critically damped driver makes a few corrections and very quickly gets to the sort of normal driving state. The over-damped driver, the over-restricted driver, restricted by fear or whatever, just can't even get from point A all the way to point B. So this is a very loose analogy, but hopefully that kind of helps you picture what the three different scenarios are. I'm going to erase this now, and then I'm going to talk about the graphs that a spring mass system might make over time. I don't know if you remember my spring mass system from earlier. It looked something like this. We had a beam or something from which the spring was attached, and then we had the spring attached, and then we had a mass attached to the other end of the spring. And the idea is to set this all up. You hook your spring to the ceiling, you hook your mass to the spring, and then you let it come to rest. And we say when it's at rest like that, it's at equilibrium. The spring in its natural state would have been shorter, but with the weight on it, we consider this an entire system. And with the weight on it, once it's come to rest, we say that it's at equilibrium. If I pull this spring down, or push it up for that matter, I'm perturbing it from its state of equilibrium. I'm disturbing that natural state. If I don't pull it, then it's just going to sit over a long period of time. This is the time axis. It's just going to sit at that height for an indefinite period of time. It's going to take some perturbation for it to move away from that height. And so if I pull it down or push it up, I think I'll push it up this time. If I push it up, then it means starting at this height, or whatever height I push it to, it will then respond to that force. Once the force is released, the mass will pull it down, right? So if I start it up here, the mass will pull it down, and it will overcompensate and come back up here, or come back up to above equilibrium. Now, depending on how far I pull it, as well as how stiff the spring is and how much mass there is in the weight, we're going to get different behavior. But what's important here is how much resistance or how much damping is applied, or how much damping exists in the system. If this thing is just sitting in a room somewhere, then the only resistance is probably air resistance, depending on what planet you're on, of course. But if it's sitting in a cage of some kind, and the medium in the cage is very viscous oil, or molasses, or mud, or something, then the same system is not going to be able to behave the same way because it has that additional force that it has to work against. So in a perfect world, what will happen is that although I'm starting by pushing this thing up here, although I'm starting up here, the system will very quickly return to its equilibrium state. And in fact, it will have to initially overshoot equilibrium, but then it pretty much just comes back to equilibrium and hugs that line that we call the equilibrium line. Okay, so this would be the critically damped scenario. This is highly unusual, highly improbable, because there's usually some kind of resistance, and how much resistance you have to apply to get it just exactly right is very difficult to determine, and it's a very unlikely scenario. Okay, here's our setup again, but this time I'm going to say that we've filled this tank, we've pumped this tank full of mud. Now, for the sake of argument, we're going to say that it's clear mud, that you can see through it, so you can watch the system behavior, but it's mud. So if I push this up now, its starting place is still going to be in the same position, but it's going to have so much resistance pushing back on the weight on the system that it's not going to be able to come past equilibrium at all. It's not going to have enough to overcome the resistance in the mud. So our behavior in this case would look something like this. In fact, it might even take a very long time to reach equilibrium, and it just never overcomes the equilibrium state. It just settles right back down to equilibrium. And it may happen over a very long period of time. It sort of depends on just how viscous or how thick that mud is. So this is a system that has been over restricted or over damped. All right, we've got one more scenario, and that is the case of the underdamped system. So in the original system, we were critically damped, which meant that whatever was in here, whatever was in the cage or the tank with the system, was just enough to allow the mass to just slightly overtake equilibrium and then come to rest at equilibrium. In other words, it didn't stay up here and it didn't oscillate wildly. It had to come beyond equilibrium to find equilibrium again, as it were. Once it had crossed that point, it just leveled off. In the case, so there's something in here. It's not just air, because I don't know if you've ever seen these in the lab. You pull a spring down or you push it up and it's going to bounce for a while, right? And that's kind of what's going on with our third scenario. And that is that we start by pushing the spring up, so it's starting at this height here, and we're going to let it drop, and when it does, it's going to overcome equilibrium in the same way that this one did, but it's not going to be restricted enough to just overcome equilibrium once and then level off. It's going to come beyond equilibrium, and that's going to be an overcompensation, so it's going to have to come up above equilibrium, and then that's still an overcompensation, so it'll have to come back down, and so on. And so you end up with an oscillation, and that would look something like this. Over time, the curve, I'm having a hard time drawing this, curve might look something like this. Not quite as high, not quite as low. It's still not quite as high, and not quite as low. Sure enough, didn't do a very good job with that bit there. Over time, it will eventually level off at equilibrium. But it takes a lot longer to get there, and it has to go through more cycles to do so. Now, remember that the critically damped situation was where we had gamma squared minus 4mk equal to 0. This one's underdamped. The overdamped scenario was where gamma squared minus 4mk was greater than 0. And here, gamma squared minus 4mk is less than 0. If you think back to our undamped experiments where we just took a spring and let it bounce, there was no damping, there was no air resistance, there was no, it wasn't sitting in oil, it wasn't sitting in it wasn't in any kind of medium that introduced any damping at all. Highly unrealistic, but if you think about that for a second, what we said back there in that video or in that section was that gamma was 0, right? We had our equation that looked something like this. Let's see, we had mass times u double prime plus gamma times u prime plus k times u equals 0. And we said for this instance, for the undamped instance, gamma was 0, so this whole term went away. Well, look at our equations here. If gamma is 0, then gamma squared minus 4mk has to be negative. So we're in the underdamped scenario. So extremely, in fact, that there's no damping at all, so we're going to be going all the way back up to the amplitude never changes, right? Here the amplitude is decreasing, but in the completely undamped case, when gamma is actually 0, this is as small as it can get. And so the graph never levels off at all. The amplitude stays as high as at its maximum, right? It always comes up to this value and it always comes down to this value. Okay, now I've gone back and copied the equations that we found on the previous screen, and I've color-coded them the same way. So if you look, they're in a different order, but if you look at the critically damped, the equation for the critically damped system, you'll notice that it's highlighted in white. The overdamped system the equation is in yellow, and the underdamped equation is highlighted in green. So for the critically damped system, actually, let's look at the underdamped system first. This is the one that's under restricted. There's not enough restriction on the thing for it to be able to settle down very easily. It takes a long time to settle down. It's got a cosine in it. So of course it's going to have an oscillation, right? It makes complete sense for it to have an oscillation. It's not just a cosine. It's the cosine is further restricted by this exponential here. And in fact, what's the best way to do this? Really, ideally, I'd have Desmos on here, and I've tried putting a browser in this software. I can do that, and showing a Desmos screen, but it just doesn't seem to work very well. Maybe I'll try to put one in at the end if I can figure out how to make that work. But if you squint a little bit, if you took your Desmos graph and you grabbed the axis and you pulled it in, that would bring this whole graph in so that it was sort of squeezed, right? So that you could see more of the graph in less space. And if you did that, hopefully you'd be able to see that there's something that kind of looks a little exponential here. I missed one there, but and this hand-drawn graph is really just a sketch. So this looks sort of exponential. And in fact, down here there's another exponential curve, and that's what's happening. We've got a cosine curve that's being squeezed by this exponential. So this equation really does make sense for this graph, which makes sense for the scenario. So the underdamped situation is the one with a cosine in it because it wiggles so much before it settles down. Now let's look at the overdamped situation. The overdamped situation is just an exponential. Okay, it's a sum of two exponentials, but it's just an exponential plus another exponential. And that, it's hard to see what's going on before 0 here. But this curve here is vaguely exponential. And that's not a surprise because the equation that we found on the previous screen actually does fit that description. Lastly, the critically damped one is a little harder to describe It is essentially exponential, but not quite, because this term here has a linear factor in it. What that linear factor is doing is preventing it from being a perfect exponential. It's not just coming straight down like this. It's making it linear, almost linear behavior for small values of t, and then exponential curvature for larger values of t. So one of the things we want to look at with these is what is happening over a long period of time. And in the case of the underdamped scenario, for very long periods of time, what's happening when t approaches infinity, the cosine, of course, would just oscillate forever. If it were just a cosine, then large values of t don't have any effect here. The large values of t that have an effect on this thing are the ones that come from the exponential. And we know that e to the t power for large values of e is 0. And of course, we've got a shift in here as well. So it depends on a lot of times we'll have a graph where the equilibrium is set to be 0, and you can certainly do that. You can set your graph up in any way that you want. So if I wanted to, I could take this t-axis and shove it up here and just call this height here 0 and let that be my equilibrium. So exponential graphs for large values of t approach 0. So it's going to approach this asymptote here. It's going to approach equilibrium. For large values of t, the overdamped system will behave like an exponential. So for a very large value of t, way out here, we're going to be at the equilibrium value. And for the critically damped scenario, we have e to the power of some constant times t. These are, I should actually point out, by way of reminder, these r values are negative. And in fact, the exponent in the underdamped case, that exponent is negative as well. And these exponents, gamma and m, are positive, so these exponents are also negative. So we have exponential decay in every case here. Exponential decay, this is the case where the whole thing is negative, but we still have a negative exponent. So we have exponential decay in every single case. In the overdamped case, we have this exponential decay that just drops straight down to equilibrium. And so because of the exponential terms, the exponential factors in both the terms in the critically damped case, you might kind of expect the same kind of thing. So as t gets bigger, without this factor of t, this linear factor, without that, the graph would just drop to equilibrium. But because of that factor of t, as t gets bigger, instead of decreasing, the function is increasing. And so it has to fight. Algebraically speaking, we're fighting with a number that's getting smaller as time goes on with a number that's getting bigger as time goes on. And of course, exponentials always win over linear. So eventually we're going to get to that equilibrium. But to start out with, that's why it drops below equilibrium and then comes back up. Now, in the undamped situation, we talked about some vocabulary that probably was already familiar from trigonometry, but has now a specific application in this scenario. For example, we talked about the period of the motion, and because it was undamped, it was one of these underdamped situations, so underdamped as to be undamped altogether. In other words, gamma was 0. So the oscillation here kept going all the way up to its maximum and all the way down to its minimum. That was the undamped scenario. And the period of that is just what we had said it would be in trigonometry. The cosine curve normally takes 2 pi to complete one cycle. So to figure out what the period is, you measure from the end of a cycle back to the beginning of that cycle and divide 2 pi by that number. We also defined the frequency of the vibration as being the value of m divided by k to the power of 1/2, or the square root of m over k. And the amplitude is just what we're used to from trigonometry. I'm still talking about the undamped case now, but the amplitude, what would be the value of the maximum attained by the graph minus the minimum attained by the graph divided by 2. In other words, it's the distance from the midline, or in this case, the equilibrium line, to the maximum or minimum. And again, that's in the undamped case. In the undamped case, remember, I'm at the bottom right-hand corner of the screen here, this value of mu told us about the frequency, and from that we were able to determine the period. Well, we don't have the same situation here. This is these graphs clearly do not have a period in the same sense that an undamped case would have, or a frequency in the same way that an undamped graph would have. But this value of mu does still determine how long it takes to get from a maximum value, in the case of cosine, a maximum value to the next maximum value. And so we call that that value there. And in the undamped case, it was called the frequency. In the damped case, we call it the quasi-frequency. In the same way, we talk about the quasi-period. The distance from a maximum to the next maximum is a quasi-period. And in this way, a lot of this new vocabulary is really quite familiar and means more or less the same thing as it does in what we're used to from our days in studying pure trigonometry. Okay, I think it's time we took a look at an example. Okay, let's just read through this and see how far we get. A mass of 5 kilograms is attached to a spring. A force of 175 newtons is required to hold the spring stretched by 70 centimeters. The mass is in a medium that exerts a viscous resonance of 10 newtons when the mass has an initial velocity of 5 meters per second. Let's just start with that. I've written out our generic second-order linear homogeneous differential equation here, the one that applies to situations like this. And I've written out a couple of formulas that we're going to use to find some of these values. Now we know mass, it's 4. Nope, it's 5. And we need to find gamma and k in order to be able to finish up this equation, finish up this problem. So I'll rewrite the problem. I'll leave space for gamma and k, and we'll go figure out what those are. We're told that the spring force is 175 newtons. So I'll write that here. And I'm going to include the units for reasons which I hope will become obvious in a moment. I'll put my negative k in. And then I'm also told that the spring constant is the constant proportionality between the amount of energy it takes to hold the spring out and the distance it holds it by. So it extends the spring by 70 centimeters. And again, I'll include my units. Now, there are two things to keep in mind here. The first one, which is fairly straightforward to think about, is that if the spring is being pulled down, when we've described down as being in the positive direction, then the spring force, the thing that causes the spring to kind of want to pull back, that spring force, that's going to be moving in the up direction, which we've described as being negative. So that means that my spring force has a negative value. The other thing I need to be aware of is that newtons are defined as being kilogram meters per second squared. And so I've got meters on this side and I've got centimeters on this side. So I'm actually just going to convert this to meters by multiplying by 1 meter over 100 centimeters. And then I can cancel my centimeter units. And I'm out of room, so I'm going to erase this and I will rewrite it when I'm ready for it. And that gives me negative 175. Now I'm using the same unit, so I can disregard them. Negative k times 70 divided by 100, or 7/10. And when I multiply both sides by negative 10/7, I get k. That gives me k equals 250. So there's my k value. Okay, now let's find gamma. The damping force is equal to negative gamma times u prime. And u, remember, I don't know if I mentioned this, or I can't remember whether I mentioned this or not. I'm using x in this problem because that is often the case. And the problem from which I'm drawing this example uses x. And so I want this to be familiar when you're going to do this problem. I don't want that to be the thing that throws you. So I'm going to change this to an x. And the first derivative, or the velocity of the function, the first derivative of the function, the velocity of the object, is directly proportional to the damping force. And we have some of those numbers as well. Let me get my pointer again. We're told that the mass is in a medium that exerts a viscous resistance of 10 newtons. There's that newtons again. This time that's in meters per second squared, and this is in meters per second. So we're okay in this case. We're going to have the damping force, the viscous resistance is 10. We have our gamma. And then we have x prime, which is velocity, right? The first derivative is velocity. We're told that that's 5. So there's that. And then I'll divide both sides by -5. And I get -2. Only here again, if the mass is being pulled down, it's moving in a positive direction, then the damping force is moving against it. So that's going to make this also negative, which means, well, that's not negative, but the 10 is negative because it's moving in opposition to the mass itself. So I get gamma equals 2. So I have that value. So now I can plug those into my equation. I have gamma equals 2, and I have k equals, where did it go? 250. Boy, I didn't leave myself much room there, did I? Let's just erase that, and I'll write this as 250 u equals 0. So there is my second order homogeneous linear differential equation. Now all I have to do is solve it. Well, the good news is we have a pattern now. We know what solutions to these things will look like under certain conditions. One of those conditions is what happens when I compare, make sure I get the right pencil here, when I compare gamma to 2 times the square root of km, or mk. Well, gamma in this case is 2, and the square root of km is going to be the square root of 5 times 250, which is 2 times the square root of 1250, and that is about 2 times 35.355. I'll leave it there for now. It's a longer decimal than that, and I will store that decimal. I will store my result in the calculator. This is just for record keeping purposes. So multiply that by 2, and I get 70.7, I'll call it 711. Okay. Now I need to compare this value to gamma. And gamma is clearly a much smaller number. So we have gamma smaller than 2 root km. And that means that gamma squared is smaller than 4 km, which means that gamma squared minus 4 km is less than 0. And this is what happens when the system is underdamped. So we now know, just with this little bit of arithmetic that we've done here and here, actually we don't even need this, with just a little bit of arithmetic, we know what the form of our answer is going to be. We know how to write the answer. We know what it's going to look like. We still have some work to do, but we don't have to go through the lengthy process of trying to solve this equation because we know what the answer is going to look like. So I'm going to erase this scratch work. Let's do this. I'll copy down the fact that gamma, which equals 2, is less than 70.711, which I claim is approximately equal to 2 root km. So I've got a note of that result, and I can erase all of this stuff. Okay. The solutions to this system look like x equals e to the power of negative gamma over 2m times t times a cosine mu t plus b sine of mu t, where mu, this is just, it's written this way for convenience. It's shorter to write mu each time here instead of, in both cases, writing out what mu equals to. And what mu equals is 1 over 2m times 4km minus gamma squared, all to the power of 1/2, or the square root of 4km minus gamma squared. This 4km minus gamma squared looks backwards, doesn't it? Because this is the reverse difference, if you will. If this is a and this is b, then the radicand, the argument of the square root when we did the quadratic formula a couple of screens ago was gamma squared minus 4km. But this result here is what happens when you have complex roots. So we know that the numerical part, that the discriminant is going to be negative. You can't take the square root of a negative number, but we do still need the numerical part of that. So to make it positive, you just reverse that subtraction problem. So this is going to give us the numerical part of the imaginary part of our complex answer. So that's why that looks like that. All right, so now let's go figure out what goes in here and here and here, and that'll tell us what mu is. In our case, mu is going to be equal to 1 over 2 times m, where m is 5, times 4 times k, which is 250, times m, minus gamma, which is 2, squared. And we're going to take the square root of that. So I get 1/10 times 5,000 minus 4. Oops, that should be to the power of 1/2, not to the power of 2. And that is, let's see, that's 4996, square root of that, all divided by 10. And that is 7.068. I want several decimal places here. 2, 3, 8. I'll go 2, 4. That gives me 5 decimal places. That should be enough. So that's my mu value. And as has become my habit, I'm going to copy that down and erase the space I did the work in, at least some of it, because all I really need now is this value here. I'm going to plug that in right there and right there. And I'm going to take gamma and plug it in there, and m and plug it in there. So let's do that next. I've moved that value to where I can access it pretty easily. I'll get rid of all of this. And then I'll just recopy the answer that I have here, except that I'm going to replace gamma with 2 and m with 5. So that's going to be 2 over 2. The pencil has stopped working. 2 over 2, so those will cancel. And then I just have 1 over 5. So I have negative 1 over 5, or negative 0.2. So it's going to be negative 0.2 t. A times the cosine of mu t, and mu is 7.07. And then I have plus b times the sine of 7.07 t. So here is my general solution, but I'm asked for an equation for the object's position, u of t, in meters, and this isn't specific enough, but I'm also given more information. I'm given that the object is displaced by 12 centimeters from, oops, not 12, 20 centimeters from equilibrium, and then released. So I have another piece of information here that I haven't used yet. Now, here's something that we need to pay close attention to in this part of the problem. The object is displaced 20 centimeters from equilibrium. So if this is my spring is attached to the ceiling here, my mass is down here, and I pull it down. In this case, I'm displacing it 20 centimeters from equilibrium. Up here, it was displaced 70 centimeters from equilibrium. But that was a previous scenario. Now we're working with this one. So I'm displacing it 20 centimeters from equilibrium, and then I'm going to release it. And what that tells me is that there is no initial velocity. I just let go. I don't apply any velocity force to it. I don't give it a push or a pull beyond just moving it down. When we say apply initial velocity, we mean pull it down if it gets pulled down, or push it up if it gets pushed up, and then push it or pull it beyond that, an initial velocity. The initial displacement is 20 centimeters. The initial velocity is 0. So now I know this as well. At time 0, the displacement is 20 centimeters, and it doesn't say in what direction. But since it's a positive number, I'm going to assume that that is in the positive downward direction. And we also know what the initial velocity is. It's 0. We're not explicitly told that, but we're told that it's just released, not released with an initial velocity of 3 meters per second or anything like that, just released. We are going to have to keep in mind our units here. Again, this is 20 centimeters. So I need to convert that. Let's see, I've got 100 centimeters here and a meter here, and these cancel. So this converts to 2 over 10 or 1 over 5 or 0.2. And with that, I have essentially a system of equations. I have the value for x, the value for this equation, which is 0.2, whenever t is 0. And I also have the value for the derivative of this equation whenever t is 0. I haven't determined what the derivative is yet, but I'll do that next. So I'm going to set up a system of equations. I'm going to find the derivative of this. I'm going to plug this set of initial conditions in. I'm going to plug this set of conditions into the original equation, and I'm going to compare them. And that's how I'm going to find A and B. To do that, I'm going to need to erase the right-hand side here. So I'll go do that and come back, and we'll talk about, maybe we'll do the derivative first. Okay, so we have x is equal to a product, e to the negative 0.02t times a times the cosine of 7.07t plus b times the sine of 7.07t. And so x prime is equal to, this is a product, so it's the product rule. I'm going to say that the first times the derivative of the second, the first factor times the derivative of the second factor, plus the second factor times the derivative of the first. The first factor is e to the negative 0.2t times the derivative of the second. Okay, so that's the derivative of a sum is the sum of the derivatives. So I'm just going to take the derivative of this and add the derivative of this. The derivative of cosine is negative sine. And the chain rule requires that I multiply by 7.07. So I end up with, in here, negative a, actually I'll write it as negative 7.07a times the sine of 7.07t plus, remember a is a constant, so the product rule applies here, but when I take the derivative of the first, I get 0. So I only need to work in one direction there. And then this b sine, so the derivative of sine is cosine, but the chain rule requires that I use that again. So I have plus 7.07b times the cosine. Thought I was going to be able to do it, but not quite. So I'll just move it down here. Plus 7.07b times the cosine of 7.07t. Okay. That, however, is just the first times the derivative of the second. Now I need to add to that the second times the derivative of the first. And I'll differentiate the first factor first. So I'm going to get plus, actually minus, because of the chain rule, minus 0.2t e to the negative 0.2t, that's the derivative of the first factor, times the second factor, which is just a cosine 7.07t plus b the sine. Now my natural inclination at this point was to tidy this all up. I was going to distribute this e, or factor the factor of e out of both of these terms, and then distribute the negative 2.2. Oops, there's a t in there that shouldn't be. The derivative of negative 0.2t is just negative 0.2. So I was going to distribute, but then I remembered what I was actually trying to do here, and that was to solve for a and b, given that I know, for example, that when t is 0, x is 20, and when t is 0, x prime is 0. So I can plug those values in now. I'm going to start with this equation, and there's a lot of it. It's all one statement there. And I'm going to plug 0 in for t. I get e to the 0, which is 1, times negative 7.07a times sine of 7.07 times 0. That's going to be the sine of 0. And the sine of 0 is 0, so that is all 0. Plus 7.07b times the cosine of 0. Well, the cosine of 0 is 1, so that's just times 1. And then I have, in fact, I'm not even going to write that because it just gets in the way, doesn't it? It's makes it a little messier. So what have I done so far? I've got my e to the 0, my sine term went to 0, this term, the cosine went to 1, leaving me with just 7.07b. So I've got that. Now I'm going to do this fact. Well, that's the end of that first term there. And then I'm going to take negative 0.02 times e to the 0, which is 1, times, again, cosine of 0 is 1, so I have just a, plus b times the sine of 0, which is 0. So I've got, when I distribute, 7.07b minus 0.2a, and this is what happens when t is 0, x prime is equal to 0. So this is equal to 0. Now I'm going to do the same thing with the original equation that I came up with. Plug 0 in for t. This time the right-hand side is 0.2. So I've got, or the left-hand side, I guess, 0.2 equals e to the power of 0 is 1. Cosine of 0 is 1, so I get just a, plus b times the sine of 0 is 0. B times 0, so that's just 0. So I can write that over here next to this one. 0.2 is equal to a. And I have a system of equations, and in fact, it's already set up. This is super easy just to substitute, right? So let's do that. 0, I'm rewriting the first equation there, equals 7.07b minus 0.2 times a, but a is 0.2. So I get 0 equals 7.07b minus, I think that'd be 0.04. Add 0.04 to both sides. Divide both sides by 0.04. Divide both sides by 7.07. And we get that b is equal to, now this is the place where I go back and say, well, it's 0.04 over 7.07, but it wasn't really 7.07. It was 7.06824. Really, it was a much longer number. So I'm going to use my calculator, but I'm going to say b is equal to 0.04 divided by that much longer, much more accurate value that I got. And that gives me accuracy in my final result. I get 0.00566. And again, it's actually much longer, a lot more decimal places on my calculator, but that should do us for now. And I have a equals 0.2 as well. So now all I have to do is take my a value and my b value and plug them in. Where am I? Plug them in here. So my final result is that x is equal to e to the negative 0.2t times a, which is 0.2, the cosine of 7.068t plus b, so plus 0.00566 times the sine of 7.068t, and that's my answer. So we'll highlight that for reference. And there we have it. That is how you solve one of these. I think we've done a pretty good job of taking them apart, figuring out what the pieces of information we had were telling us, how to use them, remembering that since spring is being stretched, it's moving in the positive direction. That means that the spring force is moving in the negative direction. So we had to change the sign there. We had to change from centimeters to meters because newtons are in meters, and this was in centimeters. We had to do that again down here. It's centimeters. I hope that has proved helpful. You will see a problem just like this on your online assignment, and now you know how to do it.